So this is the first lecture of a course on statistical experimental design. So many of the examples are set up in a biomedical research environment, although it is not only applicable to this, it can be applied to any other kind of research. So this is the outline of this first lecture. So we will see what kind of experiments we have, what are the experimental units, what is the experiment design. We will have a very large, very high overview of these experimental designs, and then we will introduce a couple of topics, bias and variance, that are very much related to these kind of things. And then at the end we will see a little bit of a statistical experiment design. Okay, so if you're interested in this topic, this is a very recommendable book, and you also have mine on the web. And let's see, so why this course? So I like this sentence: in God we trust, all others must bring data. So that means that whenever when you claim anything, especially in science, you have to support that claim with data, and that data has to show that what you are claiming is statistically significantly above the level of noise. And for achieving that, there are two parts. The first one is calculating the sample size that will give you a particular sensitivity above the level of noise, and the other one is how to organize and how to organize the experiment and how to identify other possible sources of variation that would hinder your claim. Okay, so this is what we will be doing. So for instance, let's say that you need to study 40 animals, 20 of them are female, the other 20 are male, 20 of them will be treated, the other 20 will be untreated. And you can only process 4 animals per day, so you need 10 days to perform the experiment. What is the optimal way of distributing these animals? And for instance, here you have an example of how you could distribute them. And we will come to this example later on the course. So you are studying the effect of a new drug. How will you perform the experiment and analyze the data? So for instance, here we have a crossover repeated measures design, in which you have a first group 1. This group 1 will go a pre-test, then you apply the treatment, then you test, so you can compare the measurement in this test with the one in the pre-test, and then you flip the treatment. So first you give treatment and then control, and now you apply a post-test and you can compare again. And in the second group, what you have is the opposite. So you have group 1 and then a pre-test, control, test and treatment. So the main difference is that the control and treatment, they have been flipped. And let's say that you're looking for the optimal way of irrigating and fertilizing land to grow sunflowers, and you have 5 different ways of irrigation and 5 different levels of fertilizer. How do you arrange them? How do you arrange the land to come out with the best way of irrigating and fertilizing the land? So again, this is a matter of experiment design. An important message is that you cannot fix by analysis what you have bungled by design. And we will come across again about this idea later in the course, but interesting topic is that you might have confounding variables. So that means that you have designed the experiment in such a way that you cannot say whether the differences that you are seeing, for instance, between control and treatment, are not caused by some other variable that is confounded with it, that is intermixed with that variable control treatment that you are interested in. Okay, so what kind of experiments do we have? So we have to separate apples from pears. Not everything is the same. So pilot studies are small studies, typically between 1 and 20, maybe 20 it's already too much, depending on the context, but in animals typically you use between 1 and 5. And the main goal of this type of experiment should not be statistical, should be more logistic. So you can check whether the logistics for a proposed larger study are fine, whether you can gain familiarity with the experimental material, you can ensure that the treatments are not excessively mild or too severe, you can check that the staff are sufficiently well trained in the necessary procedures, you can ensure that all the steps in the proposed future experiment are feasible. So those should be the goal of pilot experiment. If you do it from a statistical point of view, the information that you gain in variability is too weak and it is not sufficiently reliable to calculate the powers, the sample size. So probably you get same amount of information from previous publications than from a pilot study. And exploratory and experiments can be used. Typically now they are not so much used, but they can be used to generate data with which to develop a hypothesis for the future testing. So especially with animals, they are not used because it is just to see what happened. And to see what happened, it reminds me this exploratory thing, like the old maps of the world. So the explorers set out to see how the world looked like. And in a way it is fine, but they can generate, if you measure many features, many outcomes, for sure you will find features that are different between the control and treatment groups, let's say. But this picking out interesting looking differences, that is known as data snooping, it can generate useful hypotheses, but then you have to validate them. You cannot stop there and simply declare these differences to be caused by this variable that you have measured. So the problem with that is that it can significantly lead to a serious overestimation of the response, and you will have many false positives. And yeah, typically depends on the experiment, but typically these exploratory experiments are analyzed with ANOVA. So once you have a different kind of experiment is the confirmatory experiment. So in the confirmatory experiment, you have a preconceived idea of what you want to test, and so you have your hypothesis a priori, not a posteriori, like in the exploratory experiment, and then typically these experiments involve the comparison between two or more groups. So for instance here you would have a control group and then you have 3 experimental groups in which you are changing the amount of water and the salts that you use to grow plants, and you want to see what are the effects on the growth. So for instance you will measure later the biomass or whatever. So you will have a null hypothesis, and typically it is that there is no difference between the groups, but it depends on what is your problem. And if the null hypothesis is rejected at a certain level of probability, that is typically 5%, but there is nothing magical in this 5%, so you can choose other threshold. Then this means that the probability of getting the result as extreme as this or more in the absence of a true effect is 5%. So let's say that you have seen some difference between the growth of this group and the control group. So observing this difference or larger, if in reality there is no difference, is smaller than 5%. And if you fail to reject a null hypothesis, that doesn't mean that the treatment has no effect. It means that you don't have the power, or it can mean two things. So one is that you don't have enough power to detect a small difference, or that really there is no difference. In general, remind this: the absence of evidence is not evidence of absence. And experimental subjects need to be independently replicated, so each one of these plants are supposed to be independent from each other. And yeah, and we will see that these plants are independent because in principle they can receive different treatments, each one of them. So that is the definition of experimental unit. Then subjects, the individual plants, need to be assigned to groups, and they must be allocated to the different groups, experimental groups, but at random, so that you minimize the chance of having any bias. A bias is a systematic difference between groups that is caused by something else that is not the treatment itself. So as far as possible, the experimental should be blind with respect to the treatment, because otherwise we all have some interest in one of the groups, and then unconsciously we may treat it differently, or we may measure it differently. And the experiments need to be powerful, so that if there is a difference, we will have enough probability to detect it. And this power is related to the sample size. So the larger the sample size, the more powerful your experiment will be. And a formal experimental design, such as the completely randomized or randomized block Latin square, is typically used. And in most cases, it is useful if the experiment has a wide range of applicability. So in other words, if you change a little bit the different conditions, then still the differences between groups hold. And this is typically explored with factorial and randomized block designs that are part of the designs that we will cover in this course. So about experimental units. So experimental units are the smallest division of the experimental material, such that any two experimental units can receive different treatments. So for instance, if you are injecting your treatment to mice, then each animal can receive any of the treatments. So the experimental unit here is 8, because you have 8 animals. But if these animals are caged in groups of 2, and then the treatment is given in the food or the water, then both animals in the same cage are receiving the same treatment. So you can not apply the treatment to each one of the animals independently. So the experimental unit is the cage, it's not the animal. Even if you have 8 measurements, you don't have 8 independent measurements. So there can be some kind of dynamic within the cage that somehow drive the measurements in one or the other direction. So what you typically do with this is that you take the 2 measurements per cage, you average them, and then that is the observation for the experimental unit. And the same happens, for instance, when you work with fish. So the tank is the experimental unit, because typically these treatments are poured into the water. So if you have two tanks, you cannot give a different treatment to each one of the animals within the tank. So if you have two tanks, you have n equal 2 experimental units. There are experiments that are called crossover experiments. So for instance, let's say that for an animal you apply first the red treatment, then the green, gray and white, and for another animal you shuffle this order, so it is now white, gray, green and red and so on. So it is assumed that giving a treatment to the animal doesn't modify it. For instance, an analgesic doesn't modify the animal, but if you are curing a tumor, then if the first treatment cures the tumor, then the second one doesn't apply. It doesn't have anything to do. So it is supposed that these kind of treatments can be used for treatments that do not somehow interfere with the nature of the animal. And here the experimental unit is the combination between period and animal. And here, for instance, we are applying the treatment to some pregnant animals, and then we are measuring the weight, for instance, of the parts of these females. So the treatments are applied to the mothers, while the measurements are on the paps of these mothers. So the experimental unit, this is like when we did it with the cage. So the experimental unit is the cage, is the mother. So here is an even more striking example. So these kind of rats are sometimes used as a model of depression because they are constitutively depressed, while this other strain of rats are not depressive. So we want to see if there is a relationship between depression and pain sensitivity. And for doing that, we will get 10 rats of this strain, 10 rats of this other strain, and then we will test them in random order using a standard test of pain. So what is the experimental unit here? This is the strain, because once an animal is in a given strain, you cannot change the treatment. The treatment is whether it is depressed or not. So you cannot change the treatment. So the treatment, the experimental unit is truly the strain. So if you want to have a larger sample size, what you need to study are different strains and somehow evaluate how depressed they are. Okay, so what kind of experiment when we talk about experiment design, what are we talking for? Okay, so here is some objectives when we design an experiment. A good experiment should have a clear specification of the aims of the experiment. So the hypothesis to be tested should be clearly formulated before starting the experiment. So it would be a serious error to look at the results of the experiment and then adjust the hypothesis to fit the results. And this goes in the direction of data snooping. So after looking at the data, you shouldn't decide what your goal was or what your hypothesis was. And experiments should be unbiased, so there should not be any systematic difference between the treated and control groups apart from the effects of the treatment. So bias typically results in false positives, and the problem is that some other factor may be confounded, mixed with the treatment effect. And the way to here is an example of this. So let's say that you are interested in measuring the relationship between drinking coffee and cardiovascular disease. So it might appear that heavy coffee drinkers, they have more likelihood or more probability of having the cardiovascular disease. But it may be that it is not the coffee that is causing the disease. It might be some other variable that is causing both. So for instance, maybe it is a smoking. So there is a long chasm of having a coffee and smoking a cigarette. So maybe it is the cigarette what is causing the cardiovascular disease. But because you haven't measured this other variable, then you only see this relationship, but there is an extra variable that is causing both. So to avoid this kind of situations, what you have to do is to first choose wisely the experimental unit, and then randomize and blinding. So those are the main two tools to avoid having confounders that you haven't thought of. So randomization means once you have a set of individuals to do your experiment, they should be randomly allocated to any of the experimental groups, and all the probability of being in any of the experimental groups should be equal. And then blinding is because the experimenter and the data analyst and whoever is the researcher in general might have an unconscious effect on the result of the experiment. And experiment design should be powerful, and powerful in several ways. So to be powerful means that if the treatment has really an effect, there should be a high chance of being detected, and this has to so that you don't make false negatives or you don't miss many important or interesting effects. And the power is increased by three things. One of them has already appeared, that is larger sample sizes. The second one is a good control of variability. So whenever you're measuring something, you will have measurement errors, and the smaller these errors, the easier it will be to show that the treatments are effective. So here you have an example of the measurement errors of the measure of the speed of light over the years. So you see that over time measurements have become more and more precise. And this is true for speed of light, but it is also true for any analytical tool that you may use in biomedical research. And the last thing is to use sensitive subjects. So if you're measuring the effect of a treatment on diabetes, you should use an animal model that is very sensitive to diabetes. So yeah, so here for instance, there is a kind of funny representation of that. And if we are designing an experiment, we want it to have a wide range of applicability. So that means that an experiment that can only be replicated in our animal house cannot be replicated anywhere else. So probably the effect is something related to our way of working than rather to the treatment itself. So this range of applicability is explored using factorial and randomized block designs that we will see along the course. And related to this, there are a couple of interesting concepts. The first one is internal validity, and the second is external validity. So internal validity is guarantees that you are getting a correct answer. So if you repeat your experiment in your same conditions, you always get the same result. So that means that your results are unbiased, they are powerful, and you don't have false positives, false negatives. External validity is when your result can be generalized to other conditions or situations. And to do that, you should try, for instance, you can try different sexes, you can try different ages of the animals, you can try different strains, and if in all these conditions still you see a difference between your control and treatment, then that means that a difference really exists. And an experiment that uses a single strain of mice may have a very high internal validity, so the result is highly reproducible, but maybe the same results are not seen with other strains, so that means that it has a low external validity. And it is acceptable to do an experiment with a high internal validity, so that means, for instance, a single strain. But it should be clear that the external validity is unknown, so you cannot make too bold claims because you haven't tried in many different situations. And experiments should be simple, so simple meaning that they shouldn't be very complex to perform, because the more complexity is, the more chances there are that you make mistakes, that there are some bias, that there is some other variable that you have not thought of and it is affecting your result. And also there should be clearly written protocols and procedures that are known before doing the experiment. And this is, for instance, what these good laboratory practice standards require. And the same applies to the statistical analysis. So if the statistical analysis is too complex, probably you are torturing the data to reveal whatever you want. And you shouldn't start an experiment without knowing how you will analyze your data. So that kind of analysis that you will do should be known beforehand. And ideally, the results of each experiment should be analyzed before starting the next one if they are somehow connected, so that the information you get from the first experiment help you to better design the second one. And the statistical tools, they don't need to be unnecessarily complicated or sophisticated, but they must be powerful. So if, for instance, you know that your data is Gaussian, then not using parametric tests is a lack. You're lacking power. You're not using prior information that you have about your experiment, and you will be less powerful if you use non-parametric tests, for instance. So let's stop it here for this video, and we will continue in the next one with the rest of the lecture.